Hello, everybody, and welcome back to Creation Meds. Hi, we're doing a quick live show, kind of spur of the moment thing, something that I kind of like put aside to do at some point, and I have time to do it right now, so here we are. As usual with my live shows, I'm just going to give it a second before we actually start, just to make sure everything looks good on the YouTube side, which it does. So, chat, please let me know if you have any audio or visual issues. But yeah, it looks good to me. So I am going to get going here. Hi, everybody. Welcome. Tonight, we are going to do kind of a fun one. This is, right, it's not my normal Wednesday release. So, when I do it off schedule, it's shorter, it's a little looser, it's kind of the lighter topics. So, that's what we're doing here. Hi, everybody. It's great to see. I see a bunch of people saying hi in chat. Chat, I see you and I appreciate you. Thank you for being here. So what we are going to talk about here is a recent example where a creationist who I think should know better revealed that they really genuinely seem to not understand something that they really should understand. And some of you, when I get to the punchline in a second here, some of you are going to be like, well, duh. But this was a bit of a surprise for me when the conversation that I'm about to show you took place. So this occurred in the, yeah, it could be a lot of people. Could be a lot of people. It could. It is one specific person. Could be a lot of people. You're right. So this occurred in the live chat of a video that I released recently. And the subject of that video decided to, for some reason, pop into the live chat and just advertise to the world that they did not understand what I was talking about. I am, chat, place your guesses. Before I, you know what, I'm going to have, well, we're having fun here. So chat, place your guesses before I tell you who it is. And then I'll show you the screenshots and we'll kind of walk through it and I'll show you the conversation and I will show you kind of a brief explanation of the thing that I was talking about that was apparently misunderstood. Oh, you're so close. Yeah. It's close. It's close. It was, you got it. The second guess got it. It's Donnie. We're talking about Standing for Truth, Donnie Badinsky, Donnie Deals, the origin of the Donnie Deals fallacy here. So the topic that we're going to talk about here is called background selection. And background selection is one of many reasons that the mitochondrial time to most recent common ancestor calculations that young Earth creationists do, the calculations that they do to show that mitochondrial Eve existed just 6,000, 6,500 years ago. Background selection is one of many things that shows that they're wrong about that, right? So I want to be clear before I get into this and start making fun of Donnie, because that's what we're going to do here tonight. Spoiler. I want to be clear that this is not a topic that I would expect the average, like, non-evolutionary biologist to understand. Like, this is reasonably in the weeds. And, like, it's fair that if you are not immersed in the field, you're not going to understand this thing, this kind of very specific selection dynamic that we're talking about. But it is something I expect someone to understand if they kind of make it their business on the internet to debate evolutionary theory and promote young Earth creationism as an alternative to evolutionary theory and, sing from the rooftops how it's a great time to be a creationist and evolution is wrong and creationism is obviously right. If that is what you do, then I would expect you to understand some of the more in the weeds topics in evolutionary biology. And apparently that is an unreasonable expectation. So let me just briefly explain background selection, and then I'll show you the conversation and we'll kind of go from there. So background selection is the idea that if you have a DNA molecule, just a piece of DNA, like a double helix of DNA, where all of the sites in that piece of DNA are linked, which is to say they're inherited together, then if you have selection operating on one piece of that DNA, that selection applies to the entire molecule of DNA, right? Because if you have a bad mutation over here and you have a neutral mutation over here, and the bad mutation causes the individual to die or to not have any kids, then that neutral mutation that's linked because it's attached on the same piece of DNA, that neutral mutation is also going to be lost from that particular lineage. Now, the kind of solution to this, the thing that undoes this is recombination, right? If you can do everybody remember the crossing over from like ninth grade bio, where you have the chromosome from mom, the chromosome from dad, and they swap little bits, right? If you can do recombination, then background selection is less of a problem. In order for it to be operating, two things have to be very close together so that the probability of recombination in between them is very low. But if you have a non-recombining DNA molecule, then background selection is kind of a big deal, right? Because any mutation along that entire molecule is going to affect the frequency of every other mutation in that molecule because they're all linked, which means they're all inherited or not inherited as a unit. Does that make sense, chat? Since we're here live, does that make sense as like just real basic what background selection is? Everybody okay with that concept? Because that's what you need to understand the conversation that I'm about to show you. And I've like explained this in various contexts to like I had a long conversation with Rebecca about this like last year, I think, at some point. And it's a little bit specialized, it's a little bit in the weeds, but it's not actually that hard to understand, right? So let me show you this conversation with Donnie, and then afterwards, I'm going to show you exactly, like visually, why this matters in terms of the time to most recent common ancestor. Because the idea is that creationists, young Earth creationists like Donnie, want to operate, we'll say, as though the mutation rate, the rate at which changes occur in the mitochondrial DNA, and specifically in a region called the control region of the mitochondrial DNA, that rate of mutation occurrence is equal to the rate at which mutations accumulate. They build up over time. And when you remove mutations via selection, that makes what's called the substitution rate, the rate of accumulation, slower than the mutation rate, the rate of occurrence, right? Those two rates diverge from each other. The substitution rate becomes slower, and that means it takes more time to build up the number of mutations that we observe in reality when we sequence DNA. In other words, it pushes that most recent common ancestor into the distant past outside of the young Earth timeline here. So creationists need the mutation rate, the substitution rate to equal each other. And if you have what's called purifying selection, selection that removes mutations, that causes them to diverge, which invalidates the young Earth timeline. So that's kind of what we need to know to get into this. So now let me show you this conversation and we will walk through it. And then I'll show you why this actually matters in terms of these calculations. So here is a screenshot from the live chat of my Donnie Called Me Out video that I released a couple of weeks ago. For some reason, Donnie thought it would be a good idea to hang out in the live chat during that video. So here we are. Chat, is that big enough? Can you read that? Because I can zoom in and scroll, but this is the entirety of the conversation I'm going to show you. And the red box is going to show the part that I want you to focus on. So just let me know if that's big enough or if I should zoom in. I'll just give it a second so people can tell me. Kind of small? All right, we're going to enhance. We're going to zoom in here. Enhance. Okay, we're going to do, actually, hang on. We're going to do it like this. We're going to go back to this. We're going to do all of the conversation bits. We're going to select all of them, and we will zoom into all of them. Okay. Better? I think that's probably better. Everybody can probably read that now. That's as big as it can get without having to go side scrolling. So I think we're going to go with that. Okay. So this starts off with Donnie saying to me, Creationists, if mutations build up neutrally in the D loop, and the D loop is the neutral region, it's the region in the mitochondrial DNA that doesn't contain any protein coding genes. So if mutations build up neutrally in the D loop, how does the occasional detrimental mutation outside of this region help with population-wide mitochondrial DNA mutation accumulation? And I should note that the D loop is less than 10%. I forget the specific, I think it's like 8 and change percent, something like that. I think it's like 8% D loop, 92% the rest of the mitochondrial DNA, something like that, about 90-10, give or take. So he says, if you have a mutation outside of that D loop, how does it affect the accumulation inside that small region that is neutrally evolving? And my answer is very simple. I just said, oh, sorry, hang on. I got to make sure you can see it. There we go. I just said background selection. Next question. Because it really isn't more complicated than that. The answer is background selection. You have purifying selection outside the region. It reduces the diversity inside the region. That's it. Background selection. Next question. Donnie responds. He says, I'm trying to, with the number 2, because it's 1999 over here, I'm trying to, oh, thank you, Joel. Appreciate this real fast. Joel with the fact check here. Hang on. Here we go. 6 to 7% according to Google. So whatever Google's AI says, who knows if that's correct, but yeah, it's somewhere in like the mid to high single digits. Yeah, for the D loop versus the rest of the mitochondrial DNA, which in total, just FYI, the mitochondrial DNA is about 16,500 nucleotides, almost 16,600, I think. And so the D loop is apparently 6 to 7%, maybe 8 or 9% of that. Yeah. So Donnie responds, I'm trying to wrap my head around how background selection can actually remove population-wide mutation accumulation in the neutral parts of the DNA, such as the D loop. And this is where I started to think maybe he doesn't actually understand this. Maybe he doesn't. I assumed he just like knew what the argument was and came up with some half-assed reason why it doesn't work. But at this comment, I'm thinking, wait a minute, does he actually not know what this means? So let's continue here. I said mitochondrial DNA is non-recombining. That addresses the question, right? Because if you have mutations here in this little region that are neutral, and then you have mutations in the rest of the DNA that are harmful, and those get selected out, and they're non-recombining, so they're all linked, in other words, they're all linked together, then you reduce those neutral mutations. So like, I thought I was being very clear here. I said background selection. He said, I don't understand that. And I said, they're linked together. They're non-recombining. Those are the same thing, 2 different ways of saying the same thing, right? Like, I thought I was being clear. So like, I don't know what the lack of understanding is. At this point in the conversation, I thought like, okay, that should answer it. And so he responds, also, I think we're like a little bit behind here. So I think this was actually before my previous answer, but he said, also neutral rate approximates fixation rate. Not true. And so the neutral rate in the D loop, which is fast, 1 out of 33-ish, and that's like a not real number, but whatever, will approximate the long-term mutation accumulation rate. How will it not? So I think that was actually kind of in progress before I said mitochondrial DNA is non-recombining. So, the way the chat works, I think I said it right before he did. So the answer is it's non-recombining. It's all linked. So if you have purifying selection in one place, that affects all of it. And then he comes back and says, I understand, but how does that help? We have mutations accumulated in the entire population of the mitochondrial DNA in the D loop. Background selection and a lack of recombination removes those. And at this point, I'm like, he legit doesn't understand what I just said. Like, legit doesn't understand what I just said. I don't know how he's not getting this. And this is a really good comment, I think, right here. I want to highlight this. This is really insightful from Ration Extrema 3776. You can't even say he's being performative since most of his audience wasn't there. Definitely feels like genuine confusion on his end. Yeah, exactly, right? He's not grandstanding on his channel at this point. It's in the side chat of a premiere on my channel. So like his people aren't there. He doesn't have to like puff his chest, for his people in the side chat on my channel. He seems genuinely confused about how linkage plus purifying selection is going to reduce the frequency of neutral variation in the mitochondrial DNA. And judging by the chat that I'm reading right now, it seems like a bunch of people here, many of whom I'm assuming aren't actual biologists, aren't having a problem following this. Now, to be fair, if you're watching this kind of impromptu live stream on my channel, you probably have an interest in evolutionary biology and how it relates to creationism, so you probably know more about this than the average random person on the street. But still, if you're not a biologist and you have like a reasonable, familiarity with this discourse, and you can understand what I'm saying, then why can't Donnie get it? Why does he seem genuinely confused about this? So I don't know. Yeah, this is also a good question. It raises the question of why he decided to have this conversation in the side chat like this. I mean, I know he has your contact, and this is a weird venue to have these discussions. Yeah, it's because he's afraid of me, and he won't be on camera with me unless it's on his channel where he controls the mute button. It's not more complicated than that. So I've invited him like countless times to just like, you just come on anytime you want for a chat and we can have this conversation and we can go through it face to face. But he won't do that. So let me, yeah, speaking of, did he ever send you that email? No, he did say, I'll email, and then it just never happened. Yeah. So no, he won't talk to me, because, he's afraid. Oh well. So let me explain to everybody exactly what's going on here, because I think this is way easier to understand than like Donnie's making it seem here. So I'm going to switch gears here. Instead of looking at some chats, we're going to just look at some very basic visuals. So folks, this circle represents the mitochondrial DNA because the organelles mitochondria are derived from bacteria, specifically alpha proteobacteria. They have circular DNA. So this is this line represents a double helix of DNA, right? It's just twisting all around, double helix, but it's a circle of DNA. It doesn't have any start or end. It's just a circle of the double helix of DNA. And we're going to break this down. This is not to scale. I want to emphasize not to scale. We're going to break this down into two regions. The red region at the top is called the control region, or the D loop. This is the region that doesn't contain any protein coding genes. Makes up 6, 7%, 8%, something like that, mid to high single digit percentage of the mitochondrial genome. The rest in blue here, all around, the rest in blue, that's almost entirely protein coding. There are teeny little intergenic regions in there, but it's almost entirely protein coding. And that matters because it's really, really, really highly constrained. Like really highly constrained. Because the mitochondria, for those of you who don't know, who remembers, chat, hit me with it, who remembers what the mitochondria does in the cell from like 9th grade bio? Everybody knows the phrase of the function of mitochondria and why they are so important. You all want to say it. I know all of you are going to say it in like 2 seconds. Yeah, here we go. The powerhouse of the cell. There it is. We'll go with Icarus right here. Got the exact wording. The powerhouse of the cell, right? The mitochondria within a eukaryotic cell are responsible for the majority of the various steps of cellular respiration, right? Citric acid cycle, pyruvate oxidation, oxidative phosphorylation, that all, not in that order, but that all happens in the mitochondria. So if you have mutations to the protein coding genes of the mitochondria, those tend to be really bad for the cell in which they occur, because if the mitochondria of a cell are mutated and they're not generating the chemical energy that cell needs in the form of ATP, then that cell is not going to do very well. And the mitochondria, the specific mitochondrion, singular, in which a harmful mutation occurs, that mitochondrion is probably done, right? So this blue region is highly, highly, highly constrained. And we know it's so constrained because we can look at the human diversity in that region. Actually, we can look at the human diversity of the mitochondria overall, and we find that over 50% of it is 100% the same across every human. There's zero variation, which tells you the importance of it. Now, Donnie loves to cite an earlier paper by Dr. Rob Carter, Young Earth Creationist with Creation Ministries International. And that paper, Carter study, which is totally legit, it's just a little outdated at this point. But Carter found that 80% of the mitochondrial DNA is consistent across all of humanity. The actual number is lower than that. As we've sequenced more genomes, we found more relatively rare variations, but still more than half of it is 100% identical across every human, right? Which tells you the degree of purifying selection against new mutations that occur in that region, which is the blue regions, the majority of the genome. Because if you break something, it tends to kill the mitochondria or the cell in which it occurs, right? So you have lots of consistency in that region, and that indicates that purifying selection is occurring. And that hurts the creationist argument because that reduces the substitution rate relative to the mutation rate. The alternative to that is to say, well, the blue region is just like magically immune to mutations. Nobody actually makes that argument. God help me if someone started making that argument, I'm going to lose it. To my knowledge, nobody actually makes the region outside the D loop doesn't actually mutate argument, but I could see it happening at some point. Fortunately, we don't have to worry about that yet. So what I want to show you here is what happens when mutations occur in these different regions. So the mutations in the red region are tolerable, right? Those are neutral. So those two yellow circles right there that I just put in, and chat, let me know if this is clear enough for you, but I got two yellow circles right there in the red region. Those represent just variants that are present in the D loop in that neutral region. And they're present because they're tolerable. They're not breaking anything. So when the mutation occurs, there's no cost, so it just sits there and it's present in the population. Is everybody okay with that concept? So we got mutations up there. Now, obviously, mutations don't just occur in the control region. Mutations also occur in the protein coding genes. So this mutation down here, that represents a mutation in one of those protein coding genes. Now, that mutation is likely to be quite harmful, right? Because if you break one of those protein coding genes, like if you mess with cytochrome C oxidase, for example, I think that's the name of one of the electron transport chain proteins. If you mess with that protein, and I don't know where that gene is on the mitochondrial DNA, don't at me, mitochondrial genome people. I don't know, which one is where, right? But if you have that mutation down there and it breaks a really important gene on that chromosome, what's going to happen to the mitochondrion in which that specific mutation occurs? Joel, I got you. Joel, I got you right here. We're going to talk about it. This is exactly right. Probably more than Dan wants to get into, but the added layer of population genetics here, since there can be 1,000 copies of mtDNA in a single cell. Exactly. All those mitochondria are essentially competing with each other as like a population of mitochondria. So if one of them suffers a really harmful mutation, what's going to happen to that mitochondrion? Dead. So check this out. This mutation right here is bad, right? That one is harmful. So that mitochondrion, that mutation, it gets selected out of the population. Hope that makes sense. So we can just say that one's gone. And everyone agrees on that, right? That part of the mitochondrial genome is highly constrained. Therefore, you have purifying selection against potential harmful mutations, right? If a harmful mutation that reduces the functionality occurs in that region, select it out because those genes are really important. But now this gets at the answer to Donnie's question because he says, okay, I understand that purifying selection operates in the protein coding region. How does that affect variation in the control region, the D loop up at the top? And my answer, if you remember, was it's non-recombining. And he didn't understand why that matters. So here we are. Here's why that matters. Well, if this mutation kills the cell or the mitochondrion, either way, it doesn't matter, it's going to get selected out of the population. In other words, that mutation will not get passed on to the next generation. Well, this DNA molecule is non-recombining. It's not like your chromosomes that do the crossing over thing that you learned in 9th grade bio, right? Mitochondrial DNA doesn't do that. So what happens to these mutations up here when they are linked to this harmful mutation down here that occurs in one of the genes? What happens to these mutations? They're lost too, because that entire mitochondrial genome is inherited as a unit. It doesn't recombine. It doesn't do the crossing over thing. So you can't swap. You can't like break it, here and swap the top half of the circle with a bottom half that doesn't have the harmful mutation. That's how we can do it in our nuclear DNA chromosomes. We can do the swapping and we can get rid of harmful mutations that way through recombination. You can decouple the bad from the good. Mitochondrial DNA doesn't let you do that. So if you have this harmful mutation down here in one of the protein coding genes, what happens to all the linked neutral variation up here in the D loop? That linked neutral variation also fails to be inherited. Now, are those mutations up here going to be lost from the population due to this? Probably not, right? It's probably the case that other members of the population have these mutations. So what's the effect of the loss due to the background selection, due to selection against this mutation down here? It reduces the frequency of these neutral variants in the population. Does everyone see what I'm saying here? It doesn't get rid of them because other members of the population probably have some of that neutral variation, because the neutral variants are actually pretty common across all of humans. So you're not going to get rid of them. You're not going to eliminate them from the population. But what you're doing is reducing their frequency. And they're neutral, remember. So they're not going to increase in frequency due to selection, right? Like positive selection. That means individuals with those mutations have more offspring than the average, right? They're not going to increase due to positive selection because they're neutral. If you decrease their variation due to background selection, what effect does that have on the rate at which these neutral mutations achieve fixation within their populations? Because you're reducing the variation and they achieve fixation just due to genetic drift because they're neutral, you are increasing the time it takes for each neutral variant to achieve fixation. Does that make sense? If you reduce the frequency, you increase the time it takes to achieve fixation. Chat, tell me if you're following me on this, because that is the key thing here. By reducing their frequency through background selection, you are reducing the frequency of the neutral variants and therefore increasing the time it takes those neutral variants to achieve fixation within their respective populations. That's it. Because if you increase the time it takes to achieve fixation, in other words, what you're doing is you are decreasing the substitution rate, right? So if we go back up to this conversation here, I'll have to find the right comment real fast. Background populations here. It's this one, I think. Here, fixation, neutral rate approximates the fixation rate. if they're subject to background selection, they are not achieving fixation at the neutral rate, right? They are acting as though they are deleterious, even though they are neutral, because they are linked to a deleterious mutation, a harmful mutation in the protein coding region of the mitochondrial DNA. So even though these mutations up here are neutral, they are not achieving fixation at the neutral rate because they are experiencing purifying selection due to the linkage with this harmful mutation down here. And that is called background selection. And that causes the substitution rate to diverge from the fixation, from the mutation rate, right? Mutation rate up here, substitution rate down here, and that pushes the time to most recent common ancestor outside of the young Earth timeline. And that is apparently what Donnie did not understand. That's how background selection reduces the fixation rate in the mitochondrial DNA. Even in the D loop, in which most variants that occur there are neutral. So let's wrap this up. I hope that was clear for everybody watching, both the fact that Donnie didn't understand what I was talking about and the consequences of what I was talking about. Like I said, I would love to be able to explain this to Donnie's face. I would love to be able to do that, but he refuses. Like, he just straight up won't talk to me. It won't happen. The invitation has been on the table. So, it is what it is. Now, this is such a funny comment right here from Dopamine, because in my little notes of what I want to do with this stream, you'll hear where I go next. Well, now that it's been explained, surely he'll change his mind, right? Literally, I'm just going to read the next two lines I have in my notes related to this comment, which I'm going to put back on screen here, right? Now that it's been explained, surely he'll change his mind, right? Next two lines in my notes. Do I expect him to admit this works the way I say? No. Do I expect him to admit he's wrong about this? No. But I want everyone watching, creationists and not, to understand that the professional creationists, the creationists that make it their business to talk about this, on the internet, and even Donnie, I don't know if he's, a professional creationist, but it's the thing that he does on the internet, right? So let's call him a semi-professional creationist. All of these people, professional and semi-professional, ignore the mechanism I just described. And that's everyone from randos like Donnie all the way up to Harvard PhD Dr. Nathaniel Jeanson. They all ignore what I just described. They just pretend it doesn't happen in order to get the mutation rate to equal the substitution rate, which is clearly ridiculous for reasons that I have talked about at length. You could play bingo with all the reasons why the mutation rate doesn't equal the substitution rate for this stuff. And this is just one more reason. And the reason that we're talking about it tonight is it was genuinely shocking to me that in the chat of the video, the chat that the screenshots that I showed earlier, genuinely shocking to me that Donnie didn't seem to understand this. But it's not that complicated. It's not that hard to understand. So I hope everyone here understands the consequences of background selection and why it completely invalidates the creationist calculations for the age of the mitochondrial most recent common ancestor. Thank you all for watching this kind of spur-of-the-moment stream here, not during my normal time. If you're hanging out while we watch this, please remember, or afterwards is fine too, please remember to hit like before you go. Leave a comment, share this video. I'm not saying you should send this to Donnie and tell him he should talk to me, but I'm also not saying you shouldn't do that as long as you're polite about it. I think that's everything I wanted to cover tonight. So remember, I got a premiere coming, not a premiere, but I have a new video coming up in just a couple days on Wednesday. That'll be the 22nd of July, 2026. So be on the lookout for that. And I have some other stuff planned coming down the pipeline. Thanks, everybody. Hope you all have a good night. Stay healthy. And as always, don't get fooled.